Whatever you need to design, or the inspection method you need to optimize or qualify, you have to quantify the impact of influential parameters on the results obtained. The difficulty is that many parameters means many trials, and as you may have many interactions between them, it might be impossible to take them into account altogether, and not just one by one with an experimental approach. CIVA simulations are already of great help, as it is easy and fast to monitor parameters. Metamodels allow you to go one step further, as they give you access to a multidimensional analysis view, leading to an efficient exploration of inspection performances. Let's take the example of a CIVA simulation modeling a carbon steel welded pipe automated inspection with a shear wave angle beam probe mounted on a scanner at a fixed distance from the weld that moves around the pipe's circumference. This probe has to detect flows in the heat-affected zone close to the inner side of the pipe. In our case, 3 variables are considered in our performance assessment: the probe refraction angle, the distance between the sensor and the weld center line, and the location of the defect in the heat-affected zone, the position parameter being linked to the ligament one. Even if only 3 parameters are considered here, if you want to test 10 situations for each one and their combinations, it would lead to 1,000 cases, which is not reasonable to do with experimental trials. This is easier to do with simulations, but even more efficient with Metamodel. In our case, we have used only 100 CIVA simulations to generate our Metamodel, and it required only 2 hours of computation time. Based on the simulations performed, Metamodels involve smart interpolators that provide the user with a continuum of results for all combination of parameters in the range of variations defined. Let's see, for instance, the maps showing the influence of the refraction angle and the probe position for backward braking defects. The optimal angle and probe position are around the nominal values. But this graph shows you at a glance which angle range to select, if for some reason, such as access constraints, the position of the probe cannot be set as expected, and if you can control probe angles, with phased array ultrasounds for instance. It also gives you the signal sensitivity to variability or to potential positioning problems encountered on the field. You can then extract curves showing that a variability of plus or minus 3 mm leads here to an amplitude decrease of 6 dB with a 45-degree refraction angle, and that with a 50-degree angle, the same variability leads to an amplitude variability of plus or minus 8 dB. Besides, new 2D maps can be analyzed without having to run any new simulations, for instance for other defect ligaments or for combining other parameters. You can also go beyond 2D analysis plots thanks to the parallel plot display, which gives a multidimensional level of analysis. In our case, it means that you can visualize, on a single plot, the effect of the 3 parameters on the amplitude signal displayed on the right. Thanks to Metamodels, you can resample the dataset as you wish, 1,000 runs for instance, and you can consider new density functions for parameters in order to be consistent with the variability during inspections. For example, let's limit the defect ligament to 2.5 mm, and let's consider normal distributions for the probe angle and position instead of uniform ones. Parameters leading to best or worst cases can be highlighted thanks to transparency. Sobel indices diagrams are also available. You can rank the influence of the different parameters, which is really useful in an optimization or reliability study when you want to focus on the most relevant parameters to improve inspection sensitivity or stability. This is just an example, but remember that all these results have been obtained on a single computer with only 2 hours of simulation. Thank you for watching this video. If you need further information, please visit our website or contact us at contact@extend.com.